So one of the things that we want to provide you with module 3, when we start to get into layer 3 networking, things start to become a little more complex unless you have a proper way to frame the concepts. And so one of the things we'd like you to do is to spend quality time on this explanation of routing basics, right? And basically, I'm going to walk through some things today as well. In our chat, what we want to do is post this link. And you should see in chat right now this link. But the name of it is IP Routing Essentials, 21 April 2021. So this was almost a month later, this time last year. And we were reviewing some things about routes and how they work. And so what we want you to do is to begin to take in additional resources about layer 3 essentials. Remember that on layer 2, the only way to build or extend in layer 2 is to take advantage of quality of service features that were originally designed for quality of service features to tag layer 2 frames that allow for the construction of bridged domains, or VLANs as they're called, right? So you have a broadcast domain ordinarily that cannot go very much further. And what we want to do is to allow for the extension of a network, right? So we wanted to extend and expand on a network and build out so that more people can participate on a network as network hosts to share resources and information. And on the layer 2, the frame, when we talk about layer 2, we're talking about a chunk of data called a frame. Because this is on the physical network and it has to do with the data link layer and the MAC address, the only way to extend the network on layer 2 is to take advantage of features that allow you to tag a given frame for priority, quality of service. And by extension, you can identify certain frames for a different LAN or VLAN, a virtual LAN. So you can extend a broadcast domain and turn it into what's known as a bridged domain, a VLAN. And that allows you to build a little further, but you still hit a brick wall. Layer 3 is where internetworking and our global public network comes into fruition. It's where we have and enjoy our global network on a daily basis. But there are some complexities, and the best way to eat an elephant is one bite at a time. So does everyone have a copy of what I just put in the chat, the link? And can everybody click on it and pull up this screen? Because I want to make sure everybody's got this. All right.
No, Professor Kentop, I don't see it.
You don't see it in chat?
No. Can you send it again?
I sent it in chat, but if you just joined us, then what happens is that if you weren't around when it was posted, it's not there. So let me post it again. Okay. Hold on. Chat. Here we go. Oh man.
Okay, I see it.
Stand by. Okay. No, yeah, it is in there. Okay. Yeah, others are posting it too.
Okay.
Thanks,
you.
James. Yeah, feel free to post it again. You know, send it to your smartphone by text message and so on, right? Okay. In this in this module, we're going to include a series of special topics, okay? So one of the things that we encounter as we build out a global network, we've already talked about public versus private network addresses. And let me see if I can make this bigger here. So one of the things that you will encounter, and by the way, everyone should also see module 3 now. Is that correct? Everyone should see module 3 in Blackboard. Yeah, like this?
Yeah. Yeah.
Oh, okay, good. And then when you click into here, in the references, you'll see study guide addendum, student slides by Comer. So you're going to want to get as much traction as possible, and we're going to start working through the study guide in just a moment. But I want to call your attention to these additional resources that I'll post. I'll make sure everybody has it. We have special topics. When you get to global networking, the 32-bit network address, something dot something dot something dot such and such, with a subnet mask. That convention, that 32-bit, 32 ones and zeros, or 4 octets as they're called, that 32-bit address space can support 2 to the 32 public network addresses. So if we do this and we go to a scientific calculator and we say 2 to the power of 32 by using x to the y, 32, what we get are 4,294,000,000 public network addresses. That's the number of public network addresses that are presently available. And as we said before, when you get to the 10 dot something, that's a private network address range. 127 dot anything is loopback. It's reserved for loopback. 172 dot such and such, that's a class B, smaller private network address. 192.168, those are special exceptions to the full range of addresses. But we have told you that you cannot have a number higher than 255, yes? And network addresses, because of the way binary works, an 8-bit limitation. So the first octet can never be higher than 255. Anyway, with all of those public network addresses, there's only 4,294,000,000. And since the start of the internet, and how many people do we have in the world now? Anybody know? Is anybody aware?
Like around 7 billion.
A little over 7 billion.
7.75, yeah. And did you know the population of India is about to overtake the population of China? So China had the largest population, but right now they are encroaching upon, look at how close India and China are. Can everybody see that? So in China, they're trying to slam on the brakes for population increases. For India, not so much. But what we have is a case where we have a huge number of people, and we only have 4 billion public IP addresses. So the world ran out. The world ran out of public IP addresses. And we'll be talking in particular about 3 adaptions that we do in IPv4, v4 meaning version 4, the current version of IP networking that is used right now, the one with the limitation for the numbers of addresses. There are 3 essential adaptions. We're going to talk about how important it is to segment networks. So you'll notice we go to a lot of trouble to create scenarios with Net Academy and Smart Packet Tracer, and we have this kind of network and then that kind of network, and then we have routers in between. And it kind of begs the question, why the heck are we doing this? Why don't we just build one big network? And what you'll find out is that that's actually been done in some places. This actually happened at UVI 30 years ago. The people who now run the ITS shop, the people who now run the ITS department inherited a network that was built on a single class B public network address range, 146.226. something something. And they basically built out a whole series of different local networks for each building, but it's really just one large network, and they're all related in the same address space. And so it's not very much. It's segmented in concept, but not all the way. And so a lot of people, they get frustrated trying to make all the networking work, and they just build a very large network. And that is a common thing you will see, a common adaptation that you see in many places, just to make the resources manageable with, limited staff and equipment. But ideally, you're not supposed to do that. You're supposed to have separate networks for every operational interest. What am I saying? The finances. We went over this. Does everybody remember in the last module, we talked about a set of multi-story buildings, and you had some finance people in each building, and you had some administrative people in each building, and you had computer labs for students in each building, and we had faculty offices in each building. Does everybody remember that?
Yes.
Okay, thank you. I'm glad somebody said yes. If you don't remember that, go back and review in module 2. All right, so the network segments, right? The idea is that you build out separate network segmentation. It's called network segmentation. You build out smaller and different networks, and then you connect them with routers so that when you have a malware infection, has anybody ever heard of a zombie? Has anyone ever heard of like malware and it turns a client into a zombie, your PC into a zombie, your laptop into a zombie? Has anyone ever heard that?
Never heard about that before.
Okay, well, they have exploits. They have malicious software, malware, that will infect and spread to all of the connected clients in a given network. And in a case like that, if you have one big network, you're in trouble. If you have segmented networks, what happens is that local network is infected, but the rest of them not so much if the defenses are properly configured. Network address translation. We're going to talk about network address translation as a special topic because you do this every day and you might not even realize it's what's happening. But you translate a public IP address, a single one at your house or your business, and you translate it into private internal addresses. And this is better for security to have an internal, non-routable, private IP network wherever you have a business or a home, right? As opposed to just everybody being out on the internet, right? We have opposing interests on the public when it comes to the public network. And today I want to talk about the duality of IP routes, okay? And then in module 4, I'm going to move this forward where we talk about DNS. So in module 4, we're going to be talking about making things accessible, creating named resources on a public IP network, and how DNS is a critical service to make that happen on layer 3, right? And then we've got some additional information. So I'm going to be, if it's not out there already, I'm going to be posting these resources, right? I'm going to be posting these resources. And of course, we already have the student, we already have the student slides. So we already showed you that in here. Have the student slides by Comer, right? Let's take up, for the short term, this interest about the duality of IP routes. So what do we mean by duality? How many of you are familiar with the Marvel movie called Venom? Anyone?
Yeah, I'm familiar with it.
Okay. So in Venom, what you have is a case where the hero the regular human being person has a human nature, but then he also has this embedded alien nature that comes out, right? And it's kind of a dual nature. So you have these two aspects of a being, and routes are in a similar fashion. There's kind of a dual nature. We call it the duality of routing, right? So we explain what routing is and why it's important. And we want you to know each of those dual natures, right? We want you to distinguish between dynamic and then static routes. We want you to recite specifics of the protocols used for dynamic routing. So let's back up a little bit. What I showed you last week in Packet Tracer, where I build my own internal network and I create routes in that network and I define explicitly what and how I want the information to flow, that is a static route. When we talk about the internet in a global sense, and we talk about outages and catastrophes and wars and destruction of internet backbone, there's like this self-healing dynamic routing process that occurs. Has anyone ever seen the movie Terminator with the liquid metal kind of thing? The villain that's got, like, he can take on different shapes and such.
Yeah, the T-1000.
Yeah, the T-1000 is made out of liquid, and so he can kind of become different things. Well, if you were to use a nuclear weapon on part of a country and completely destroy the internet, instead of that crippling the entire internet, what would happen is that the routers on the backbone of the internet are rigged for, they're configured for more so for dynamic routing. And there is a protocol that allows them to dynamically recreate different routes from one point to another. So if we had a picture of the United States of America right here, and over on your left was the West Coast, and over on the right is the East Coast, and here's Chicago in between. If a nuclear weapon, heaven forbid, took out the whole Chicagoland area, and people had to send packets from New York to, say, Montana, they could use dynamic routing, and the internet would heal itself, in a manner of speaking, create new routes so that somebody would send that packet that used to go through Chicago, but now it's going through St. Louis. Now it's going through Ontario. Now it's going through Dallas, and then back up to Montana. Does that make sense? Kind of, sort of, maybe. Okay, we want you to understand why static routes are important to understand, why you would want to use them sometimes. A caveat means an exception, right? So we want you to provide a case where you want to use static routes instead. And there, you want to know what the exceptions are, the important exceptions are to that basic rule, and the basic format for building a static route, because there's a basic command. And I want you to know the basic command by heart. Rote memory. When you go into the packet tracer, I want you to be able to do this from memory, because it's that important. You can also, and here's the weirdness, you can also take your own PC. And I don't want you to do this right now, but I do want to demonstrate here just in a minute. You can basically get a command prompt with administrator privileges and use similar commands, and then turn your own PC, your own gaming console, your own laptop into a router, because you implement a static route, and then when packets hit your system on the layer 2, when everybody broadcasts frames, right? And those frames are considered on that layer 2, if it has the right IP address inside there, embedded inside, encapsulated inside, when that's unpacked and looked at, your own machine can say, oh, that doesn't belong here, that belongs outside. And so you can kind of turn your own equipment into a router. That's not considered a best practice, but in a pinch, it's actually pretty cool. You can do some things to establish resilient connections after a disaster, if you know how that works. Okay, we also want you to be able to specify the essential components for a simple routing solution. And this is where we talk about your hands-on, right? So the best way to learn this in some cases is just to do it. We want you to be able to relate specific criteria for a successful static routing solution. So we want you to know what the main pieces are and then how they're, to what specification are they configured? That's what we mean by criteria. Are there any questions at this point about what we're going to be doing and reviewing at this time?
No questions.
Okay, so let's explain what routing is and why it's important. Okay. Without routing, MAC address tables would be too large to function. The MAC address table on layer 2 on a switch, well, yeah, you could build a switch that's got enough memory for a larger and ever larger network, but eventually you'd run out of memory. You can't store specific information for 4,294,000,000 devices on every network device. Are you kidding me? I mean, do we know how much that would take, right? How much memory would that take? Just too much is the short answer, right? Just too much. Give me 1 second here. All right. Good afternoon, Kevin. Are you rejoining us? You having issues with the connection or something?
Yeah, my laptop was acting a little wonky for a second, but it just caught itself.
Yeah, glad you're back. Okay, so MAC address tables would be too large if we didn't have routers. A local area network has no way to pass an IP packet beyond the broadcast limit. Now, we said a broadcast domain is the local area network by definition, right? So if you have an IP packet that belongs to another network, without a route, you have no physical means to route or redirect that packet out. Now, in just a moment, we're going to talk about how private internal network address ranges are so good for that reason. Let's repeat that. When you use NAT and you use a private internal non-routable address range, even with routing, what happens is somebody tries to redirect your data outside the network because they're bad people and they're trying to steal your private, personal, protected, sensitive information, your finances, your healthcare information, whatever, right? And they can't, even when there's routing. So we're going to get back to that when we talk about NAT and the advantages of NAT, network address translation. All right, at its core, a basic router performs just 2 functions. Now, I want you to be able to reflexively, just like the routing command we're going to review in a minute, I want you to be able to tell me what those 2 functions a router performs. And these are highly specialized, highly evolved, meticulously adapted, specialized equipment, right? So the firmware and the software that's developed by network companies like Cisco and Netgear and D-Link and HP and Alcatel and let's see, what are some other ones? Nortel, Siemens. These are all big networking companies. Huawei. This is a Chinese company that's been accused of playing copycat with Cisco, right? These are all companies that basically produce these routers, and making them more efficient and faster performing is a big deal, because when you think about the data that flows across the internet, it's huge. I mean, there's no way for the internet to work properly without proper routing and without proper equipment installed. But at the heart of it, a router just does 2 things, right? It looks at a packet and says, hey, is this local or not local? It's a very binary decision. It looks at the packet of information, splits out the header, looks at where it's going, the destination, and it says, oh, wait a minute, that's not this network, it's outside. See, the network identity matches the local network or it doesn't. It's the subnet mask thing all over again. It's the subnet mask thing all over again. Happens in the blink of an eye. It says, hey, wait a minute, this is not local. If local, nothing happens. The packet is dropped, meaning the router doesn't do anything to ship it outside. So that gateway is a closed door when it's local. Let me repeat that. We all need to say that. When it's local, the gateway out to the internet up here, if we had a gateway up here and everything else on my screen was a local network, and outside was up here in the corner, you got to get out to the internet, then that gateway half the time is a closed door when it's local. When a packet is local, it just says, okay, I'm not going anywhere with this. I don't even have to think about it. And it drops the packet. If it's not local, it passes the packet inside the router where it looks at the routing table and it decides based on the routing rules and table, okay, what am I doing with this? We have something called an access control list that works hand in glove or in a very complementary fashion with the routing table. The routing table is a listing of routes that are executed in an order. So a packet comes in and it says, does this rule apply? Yes or no? Well, that one doesn't, but what about the next rule? Yes or no? Yes or no? There are also a set of security measures called access control lists or ACLs that work with those routing rules. If an access control list criteria is triggered because of a security concern, then the routing may go, it may route that packet to a security device for analysis, right? Any questions about that? So if it's local, nothing happens. If it's not local, then it looks up a route and then it relays out. It looks up a route and it relays out. R and R. It looks up a route and it relays out. R and R. That's what I mean by R and R, not rest and relaxation. Everybody know what I mean by R and R? Everybody
Yes.
with us? Okay. So put another way, routes between nets are called internets. Now, this is huge. It's called the internet, not the intranet. Okay. Routes between networks create this concept called internets, in between networks. Routes between networks is literally equal to the internetworks. If it's within a network, that's called intra. If it's between networks, it's called inter networking. And routers and routing are the very reason that we have internets. Now, the term internets does not necessarily mean the global public network. If you talk about internets, and we're not talking about the worldwide, everybody all tied together, that phenomenon, a capital I is used. When you're talking about a collection of networks that are connected with routes, then you use a lowercase I. Does everybody understand that?
Yes.
Okay, good. Because if I see you submitting detail about the internet as in the global public network and it's not capitalized, I'm going to comment on it because I don't want you getting, it's considered good form to understand the distinction between the two. Okay. And I want you to hold your head high in any technical discussion with future employers or colleagues, right? But when you talk about internets between networks, and it's not the global public network, but it's, hey, we have routing rules between the local network in the Chicago office, the local office network in New York, the local office network down here in Miami, Those are internets with a lowercase I. Okay. Now we're going to distinguish between dynamic and static. We've already talked about this somewhat. So dynamic routes change as network conditions vary. It's very fluid. Yeah, it's like a fluid. Delivery path can be different every time. And delivery is guaranteed for that reason. Now that's huge. Let me say that again. And I'm going to be very dramatic here. If we didn't have guaranteed delivery, I don't know that the internet would have ever taken off. Not the way it is now. The fact that we have guaranteed delivery is a function of this dynamic nature, because if we can't get to Montana through Chicago, we're going to get there through St. Louis. We're going to get there through Oklahoma City. We're going to get there through Ontario. We're going to go through Dallas. We're going to go to Istanbul and then through Peking, China, and then through Honolulu, and we'll come in from the west side down through Alaska. That's what we're going to do if we have to. And it's been done. A packet can travel the world, and that's why you can guarantee delivery, which is very cool. But it's also frustrating. If you ever wondered why things kind of delay or take a while, that's one reason why it does. It provides for multi-path delivery. And you'll notice that when I post this slide, this set of slides, it's a Blackboard, if it's not out there already, this is a link, right? So you can click on this, it'll open up a YouTube that explains multi-path delivery, public transport. Very cool. It's not a very long video, right? We're not going to look at it right now. In the interest of time, we're going to keep moving. Static routes. They're established as an anchor that does not vary. It's like stone. It's constant. It doesn't change at all. Your stuff either meets the criteria of that network route or it doesn't. It's very black and white. Okay, I have a route out to this network. Is this packet headed for this network? Nope. Then that route doesn't apply. And in a sense, it's like an anchor. We don't keep passing packets all over the place to try to get them there. In this case, where we use static routes, we're creating boundaries. We're creating barriers, intentional ones. We're creating limitations. We're building a network for resilience. And so if plan A fails, then there's a plan B route, and there's different equipment that carries it. So we use static routes for definition, where unchanging, immutable capabilities are concerned, right? We want to use static routes whenever we're doing that. And I'm gonna try to trick you on assessment questions. I'm gonna say, hey, you got a guaranteed delivery. Am I looking at dynamic routes or static routes? Well, dynamic routes are better. Well, hey, I need to use something like an anchor, and if a packet doesn't meet the criteria for a specific network to be routed out to that network, which should I use, a dynamic route or a static route? You want to use a static route, where you specify which routes go where. And if that packet doesn't meet any of those criteria, it's just dropped. It's erased, it's deleted. It's like it never existed, right? Which can be incredibly powerful for security. And nobody gets this. They don't set up access control lists on routers like they should. So I'm going to get on my soapbox for a second here, and I'm going to tell you that after 20 years in industry, working in hospitals and places where the technology, you can't do your job without the technology, right? You just can't. This kind of stuff, people need to understand better. And let me tell you, hackers know it. They know how to set up a static route temporarily on somebody's PC when they hack their PC, so that all that information is routed out to them, so they can read all your Kool-Aid, right? So a lot of power here in these. Any questions about the difference between dynamic and static routes?
No, no question.
So in this case, the delivery path is identical each time. It's not a different path. It's identical. It's the same each time. And you guarantee the route that data passes, right? Do you want data to pass by a certain route so a piece of security equipment can filter it for malicious traffic? Yeah, you might. You might want that digital traffic to go by one checkpoint in particular. It's no accident that one of the largest and most prominent manufacturers of industrial strength network firewalls is called Checkpoint. Because you create an identical path, it guarantees the route, the data flows by the firewall and through the firewall, and the Checkpoint firewall can say, hey, wait a minute, there's something malicious in here, okay? It provides custom dedicated path for filters and private transport. You want to get around hackers, you want to frustrate the bad guys, spend some time learning this stuff and doing this stuff. And I guarantee you'll have them scratching their heads. It's kind of like a giant chessboard, and it's the coolest chessboard in all the world. I just want to impress on you, if you haven't been impressed already, just how profoundly different these two related functionalities truly are, and how each covers an essential need. Oh, we have a nuclear war. How do we get the message through? Dynamic routes. Oh, we have bad guys on our network. How do we make sure we catch them? Static routes. Yeah. We control what's fluid and what's solid. Why should you care? When you create network applications, you may need to specify a given mode of delivery, high security environments. We talk about secure coding all the time. In fact, this is one area where computer scientists can do so much better. It's sick. People think in very rigid terms about, oh, I'm a coder and I'm creating a program, and it's a multi-layered solution. And yeah, I know about all of the network models and the IP stack and all this kind of stuff. But there are cases where highly secure environments have never had an application created by an up and coming computer science graduate, perhaps from UVI. And they say, you know what, I'm going to specify in my code that the packet cannot be delivered by a dynamic versus a static route. It's going to check for certain conditions, and my transmission will only occur if certain criteria are met. True or false, right? You have large data sets, right? Supercomputing data sets. When we say SC, we mean supercomputing. So you got to be able to specify how those things are going to occur. Why should you care? If you reroute and corrupt the data that goes into a supercomputer, then we all think that the hurricane's going to land here, but it doesn't. It lands there instead, and it devastates people, right? Is everybody with me? We're almost done. Just want to finish.
Yeah, I'm with you.
Okay. So almost any connected device that uses IP networking includes the ability to create a static route, and that's good and bad. We've already told you about that. So what does routing provide to land users? Essentially the means to control traffic. Can someone answer this question based on what we just covered? How is a dynamic route different from a static route? Any quick explanation will do. I need a volunteer. How is a dynamic route different from a static route?
A dynamic route would have multiple, whereas a static would have only one.
Right. Multiple routes, fluid routes, flexible routes. A static route would not be flexible. It would not have multiples. They would not be spontaneously generated on the fly. Yeah, very good. Thank you. Okay, now we're going to stop right here. And on Wednesday, we're going to talk about the protocols for dynamic routing. What have we done today? We have explored at considerable depth what routing is and why it's important. We've distinguished between the dynamic and the static routes and why they're both special and why you should know the differences between them and how that could lead to a very high paying job as a newly graduated computer science alumni of the University of the Virgin Islands, because if you understand this difference, you can create secure network applications that require specific conditions to be in effect before sensitive data is transmitted or received, right? It's called safe computing. All right. Does anyone have any questions or concerns before we close for the day? Okay, hearing none, I'm going to go ahead and stop sharing and stop recording. And I'm going to ask again for questions.